So I remember the exact moment I became a neuroengineer. Episode 5, Empire Strikes Back. I was 7 years old when my parents finally let me watch it. There's an epic battle between Luke Skywalker, the good guy, and Darth Vader, the supervillain. Plot twist, Darth Vader turns out to be his father. Sorry if I ruined that for you. A few scenes later, Luke Skywalker is in a medical bay. He's lost the battle. His dad has cut off his arm. And there's a team working to create a new arm for Luke Skywalker. It's a robotic arm that Luke Skywalker can move just by thinking about it. That changed everything for me. It was my senior year as an undergraduate engineering major where I discovered the field of neuroengineering. I heard about this amazing research being done at Duke University, led by Miguel Nicolelis, who had figured out how to read electrical signals from a monkey's motor cortex. He then processed those in a computer and fed them into a robotic arm such that the monkey could move the robotic arm just by thinking about it. Return of the Jedi. I had to be part of this. I applied to schools, and I ended up in the joint MD and PhD program at Duke University. And my goal was to take this technology and use it to transform and improve human health. I was in my second year of graduate school when everything changed for me. I got a call from my mom. She was frantic. My uncle was missing. It'd be about 9 months before we found him in an alleyway in another continent. He was delusional, paranoid, hallucinating. My uncle had schizophrenia. And so from that moment, I decided I would dedicate myself to trying to take this technology in the area of brain-machine interface and coming up with treatments for those suffering from devastating psychiatric illnesses, people like my family. Now, I had a roadmap from my colleagues in cardiology, so I thought it would be a straight linear path at 22 years old. Imagine you had pain in your chest. You might go in the emergency room. And the doctors would put 12 leads on your chest to record electrical activity. Because they know what those patterns should look like in the normal case, they can diagnose certain subsets of disease. Some people might get a medication. Some people might get a stent, as the last speaker pointed out. And some people, in some cases, electricity is the medicine. In fact, electricity is such a ubiquitous medication, we all know pacemakers, they're everywhere. And so my goal was simple. I would develop a technology where I can record from 12 brain areas inside the brain at the same time. I decided to use mice as my model organism because we can change the genes of mice to give them risk genes that give risk for mental illness in humans. We can expose them to stress or drugs of abuse. And then I collected these electrical signals and worked with teams of folks, electrical engineers, to use machine learning to understand these complex patterns and how they signaled health and disease. There's a clear lesson that we learned for this. The codes for emotional function weren't just in one brain area. In fact, they were how brain areas work together. So let me give an example. Imagine you have a brain area that has activity at a pace. The brain can tell the difference between this, and this. All of those codes are different. And so it meant that we had to understand how parts of the brain were working together and control it if we were going to come up with treatments and therapeutics ultimately. Now, the brain has a way of controlling this timing between cells. In between two brain cells is a space. It's called a synapse, where biomolecules control the timing between two cells. So my perspective as an engineer is this is pretty simple. All I have to do is make a microchip synapse. And we engineers, Miriam pointed this out earlier, and Paul as well, we engineers call this a closed-loop system. Essentially, you record electrical activity from one part of the brain, process it in a computer, and then use it to drive the downstream cell. So at this point in time, I'd finished my psychiatry training, and I had an observation in the clinic that folks that kept coming in, whether it was the first episode of schizophrenia or bipolar disorder or depression, stress was there. And it turns out stress is there at the onset of psychiatric illness. As we've all appreciated during the pandemic, stress makes psychiatric illness worse. And so what I wanted to do was understand how stress triggered the emergence or worsening of illness, and then figure out if I can create a closed loop microchip pacemaker to improve resilience in the brain, with mice as the model organism. So we started on this adventure. It took about 15 years to figure out how to do this, and ultimately, we were able to create this type of system. We targeted a brain circuit in the brain, a brain circuit that mediated resilience, and we were able to make the mice more resistant to environmental stress. I was so excited when I saw the first results that I hopped on a plane, flew to Ghana in West Africa, where my family is, and I went to show my uncle the results. I had a perfect PowerPoint made, beautiful slides just like the ones I've shared with you this morning, and I walked my uncle through the presentation. And at the end, he asked me a question that stuck with me. He said, "This is great. I'm so hopeful about the future. Tell me more about how this is going to help people in the third world." And I was dumbfounded. I had no answer at all. The more I thought about the scale and the scope of psychiatric illness, whether it's 200 to 300 million people suffering from depression, or 3 out of 4 teenage girls in the United States of America were complaining of anxiety and persistent feelings of sadness, it was clear that the technology I was working on just wasn't going to scale. If you look across the burden of illness, we simply don't have enough TMS machines, focused ultrasounds, MRIs, or deep brain stimulators in the United States of America to treat these illnesses, let alone in the world. So I was really challenged at that point in time to take a radical approach. I had to engineer a type of synapse that wasn't based in microchips. I had to think about something that was scalable. And the answer was biomolecules. So it turns out we have some additional lessons that we learned from our friends in cardiology. Yes, the heart has nerve cells which release neurotransmitters like norepinephrine, but it also has a process that allows electrical activity to move directly from one cell to another. They're almost pores. We call them gap junctions or electrical synapses. It turns out a team of scientists about 4 or 5 years earlier had actually found what the biomolecules were that constructed these electrical synapses. They put them in worms between 2 cells. It caused the activity of those 2 cells to synchronize and change the behavior of the worm. Now, the problem with using this in a complex organism that has more than 302 neurons, like we humans do, is these biomolecules, these patches, are like stickers. So we spent some time in the lab re-engineering these connections so that they would work like magnets with a positive and a negative end. We then went back and actually made a protocol to put these in mice, targeting the exact same circuit that we'd found before that increased resilience. I was on a plane flying across the country, and I got an email from a senior scientist in my lab, and it worked the first time. I landed, and I ran straight to the lab because I wanted to see it by myself. I walked in the door, walked up to the cage of mice, and you know what I saw? I saw nothing. I stared at the mouse, and unlike the experiences I'd had with patients where I could walk in the room and tell that they'd gotten better, I couldn't tell anything from the mice, right? I couldn't tell if they were happy or sad. I couldn't tell if they were guilty or what their concentration was. I couldn't get any sort of emotional feedback from the mice. And I suspect it's not just me, right? If a mouse ran down the aisle, we're in New York, so if a rat ran down the aisle and had a piece of cheese, none of us would be thinking about the innate happiness of the rat, right? So I'm going to ask you a question. Everyone, put your hands up if you have a dog. Now, I'm not going to ask you to pat your underarms. Hold your hands up. Keep them up. And now only put your hand down if you believe that your dog has feelings. Okay, so every hand went down, right? Because mice don't pass the Turing test, but it turns out that dogs do. We believe that they have feelings. And at the core of psychiatric illness, despite whatever disease it might be or illness it might be, there's social and occupational function. And dogs are the species that work and socialize with humans the way we work and play with each other. Suddenly I started seeing dogs at airports, right? I see all these dog jobs. And I went to give a talk at a vet school, and I'm talking to the vets, and they said, "Wow, it'd be great if you can do this work in dogs." I said, "Absolutely not. They'll shut down my lab." And they're like, no, we're putting our dogs on Prozac. And in North Carolina, there are all these mixed breed dogs that are mixed breed with pit bulls. And they get anxious, and they get aggressive, and then we euthanize them. So anxiety and aggression are terminal illnesses in dogs, and if you can figure out how to adapt this technology to work in dogs, you'd be helping the dogs. So I approached vets to start building out a collection of scientists to take on this project. And after about 3 years, we were able to bring on our most important collaborator of all, the Humane Society. And we're getting ready to launch this effort with the idea that my goal, my dream is clear. I want to help my family. But I now believe that if I do work and advance work in dogs to help the emotional well-being of dogs as the sole endpoint, I'll do much more for my family towards the goal of creating a therapeutic than using mice to help them directly. So I'm grateful to be here with all of you all. I hope that some of you all would join my team of pain specialists, scientists that work on anxiety and aggression, government officials, and the Humane Society on this adventure. So God bless you all, and God bless the United States of America.